Welcome, everybody. I'm David Coates, and I'm the chair of this year's ACM SIGMOBIL Rockstar Committee, and I'm pleased to introduce this year's Rockstar winner. So the Rockstar Award was created by ACM SIGMOBIL to recognize an individual who has made recent outstanding research or product contributions to the field of mobile computing during the early part of that person's career. Let me give you a little bit more background about that. This award is designed to recognize the technical contributions made in the early part of that person's career, resulting in notable influence on the field. And we define early career to be within 10 years of receiving their highest university degree or younger than 40 years of age at the time of nomination. And the committee focuses on the impact of the candidate's work in creating promising new ideas, paradigms, and tools related to mobile computing, looking at things like the depth and impact and novelty of those contributions while they're making their selection from a pool of nominees. So this year's selection committee includes myself as chair, 3 other senior researchers from the field, Morley Mao, Mary Baker, and Tenzin Chowdhury, each of whom has a staggered rotating 3-year term, and then the 5 most recent rock stars, which I actually highlight here on the next slide. Many of you, like me, have had the pleasure of seeing these Rockstar winners present their work at a previous MobiCom or MobiSys. Most recently, Xia Zhou presented her Rockstar lecture at MobiSys 2020 in recognition of her being named the 2019 Rockstar. So it's my pleasure to announce the 2020 Rockstar winner, Nick Lane, who has been cited, quote, for contributions to the understanding of how resource-constrained mobile devices can robustly understand, reason, and react to complex user behaviors and environments through new paradigms in learning algorithms and system design. Now, many of you know Nick. He's well known in our community, but here's a bit more background. He's from New Zealand, where he got his bachelor's degree. Then he came to the US for a Master of Engineering at Cornell University, and then a PhD right here at Dartmouth College. Then he went on for several years in industry research, first at Microsoft and then at Nokia Bell Labs, before starting in academia as a senior lecturer at University of College London. He later co-founded the Samsung AI Center and became an associate professor at the University of Oxford, and then very recently, just in the past few months, moved to the University of Cambridge. So he's received many other awards in the past, including the ACM SIGMOBIL and the ACM Census Test of Time Award in 2018 for his work on the SenseMe smartphone sensing system, and several times Best Paper Awards from MobiCom 4 times, and IPSN, WristSense, MobiCase, and PhoneSense. Now, the committee recognized his many contributions across different areas, but in particular around smartphone sensing and mobile deep learning, much of which has translated into impact in industry. And he's also been very helpful in our community, most notably as the PC chair of Hot Mobile 17 and Census 18. In the nominating statement and the supporting letters, there were lots of great things said about Nick, and I pick out just a few of them here. One called him one of the key pioneering academics in mobile deep learning. Another said that he pioneered the study of commercial off-the-shelf smartphones for complex activity and context recognition, and indeed called him one of the most foremost intellectual leaders in activity recognition today. Now, Nick's research is actually very broad in some ways. He's, quote, touched all layers of the stack. And his nominator or his supporting letters included some co-authors, one of whom said Nick was the key driver in terms of ideas as well as implementation. And in short, his work is simply stunning and breathtaking. So again, it's my pleasure to recommend to the chair of ACM SIGMOBIL, the 2020 Rockstar Award winner, Nick Lane. So to you, Marco.
Thank you, Dave. On behalf of the SIGMOBIL community, my heartiest congratulations as well, Nick. This is one of our most important awards because it recognizes the new generation of SIGMOBIL leaders, and we are incredibly proud to have such a well-deserved winner. With that, I'll hand it off to the previous winner from 2019, Xia, who will recognize you in our tradition.
Great, thank you, Marco, and congratulations, Nick. So as you may know, as a SIG Mobile tradition, being a rock star comes with winning a hat, and that's what I'm here for. So I prepared these shiny, not very well, shiny rock star hats that I hope to hand to you in person in the near future, just like how you are shining in our community for your research contributions. Congratulations again, Nick.
Thank you all for this award. I'm very humbled to receive it, and I feel that it's really a reflection of how lucky I've been to work with some fantastic colleagues and students, and the help I've received and guidance over the years from some amazing mentors. And I think I should also mention that it means a lot to receive this award from SIG Mobile. It's the community that I started in as a PhD student, and I've found it not only to be a place where people sort of really study, world-changing ideas, but it's also a place where the community is very open, inclusive, and welcoming. So this really means a lot. Thank you all. Thank you for this introduction. It's certainly an honor to give this talk today. And before I begin, I really wanted to start by saying I hope that everyone who is listening, as well as their families and their friends and colleagues, are well and healthy in these challenging circumstances. Now, before I also begin with the material of this talk, I really want to fully acknowledge that so much of the work and ideas I'll be presenting today come directly from a fantastic set of students and postdocs I work with in my lab now at Cambridge, as well as a tremendous group that we've built over the past 2 years at the Samsung AI location in Cambridge, which is also focused on distributed and embedded forms of machine learning. I note that both of these photos were taken just last Christmas, and this is probably the last time that we were all together in these respective groups. Now, today I'm going to speak about my passion, which is efficient machine learning, and that is attempts to take state-of-the-art forms of machine learning that were conceived to run on data centers and understand how we can make them run directly on mobile and embedded devices, overcoming a large number of energy, memory, and compute constraints that stand in our way. Now, you might not realize this, but you probably already use efficient ML techniques on a daily basis if you use your smartphone. Every time you do, for example, a search for an object or a face within your photo album, chances are you're using a different type or a certain type of efficient ML to perform this action locally if you have a high-end phone. What this affords is a level of protection to the user in that their sensitive photos do not necessarily have to go to the data center for these machine learning based search and recognition processes to be applied. There's a variety of the functionality that you find in smartphones today can be enabled or are in fact enabled with efficient ML techniques. And similarly, it's not just about smartphones or wearables. If I think back to when I used to commute between Oxford and Cambridge, I would drive through a town called Milton Keynes. Now, Milton Keynes has one of the largest delivery robot networks in the world. So these robots deliver, for example, things like groceries, and systems like these can be profoundly impacted through efficient ML technologies. For example, the robots are able to run their perceptual algorithms entirely locally, or their navigation machine learning techniques, again, entirely locally, where they can be far more robust and resilient to things like network outages relative to if they had these solutions completely dependent on a data center and the connectivity to that data center being the weak link in that chain. What I've been alluding to is a series of benefits to using efficient ML. First and foremost is user privacy. Second, I mentioned things like robustness to the device. But third and fourth, it allows us to bring the strongest state-of-the-art algorithms to what are often the hardest problems, namely the types of data, images, audio, or other types of sensors that our mobile devices experience in complex environments. And it furthermore allows us to drive down, lower the energy and the latency of performing important mobile device-based user experiences. Now, when I used to give talks of this type, I'd always have to be more aspirational, tell folks about what we might be able to do in the future. But lately, there's been a series of success stories I can easily point to. This happens to be one of them. This is an application called Seeing AI, released by Microsoft. You can download it today and start using it. What it does is tries to help those that are sight impaired have a greater understanding of the world around them. It enables a large number of state-of-the-art vision algorithms to run completely locally, so very safe for the user in terms of their privacy and leaking sensitive images, and it can do things such as what you see in front of you. It generates a very convincing caption based on the image presented that can then be spoken aloud to the user so they can understand what's right in front of them. Now, what's important though is that this application is enabled by on-device technology that we're talking about today. And if we look back in the past 4 or 5 years, if I bring the slide up, here is a laundry list of breakthroughs and techniques that have been developed in this direction. On the left-hand side, I've listed a number of the techniques and methodologies that my group have developed over the years, but perhaps you want to spend more of your time looking on the right-hand side, which is a collection of methods that also came from the broader community as a whole. Now, collectively, these techniques allow really transformative abilities for us to deploy state-of-the-art machine learning on these devices. And this has really happened very fast. In the last 3 to 4, 5 years, where we've seen real change in what is actually possible. At this point, it might be a good time for me to illustrate how some of these techniques work. I'm going to pick on a very simple technique, that of node pruning. It's also a very successful technique. So on the left-hand side, you see a fully parameterized neural network as it might come out of a training process. Now, what people discovered was that if you carefully remove the weights and the nodes of a neural network, and you're very judicious about which ones you remove, it's possible to prune back potentially 95% or even more of the entire network and have it still have high levels of accuracy. People refer to this and other related techniques as forms of model compression. There are ways that you can describe the parameters of the model using fewer number of bits. There are system techniques that can further enable models to be more efficient. But what really is important is how these techniques enabled us, or had this property whereby you could really squeeze down the network significantly, 95% or more, and still maintain high levels of accuracy. And these have been breakthrough types of results that allowed us to deploy on things like smartphones. Now, this is a picture of the Tenzing Hillary Airport. It's in Nepal. It's a great place to go if you want to climb Mount Everest. But what's unique about this airport is that at the end of that runway that you see at the end of this picture is a 700-meter sheer drop. And I'm showing you this picture to ask the question if perhaps efficient ML is in this situation and we don't even quite realize it yet. The reason I want to say this is that we've made dramatic progress in the last few years, but are the techniques that we're using today and investing in so heavily going to be sufficient to continue the types of efficiency breakthroughs and deliver the types of smart devices that we've grown accustomed to seeing in the last few years, year on year moving forward? One reason why there might be pause for concern is actually grounded in the fundamental reason why this area is hard at all. One of the reasons why doing efficient ML is so difficult is that modern machine learning has an incredible insatiable desire for increasing amounts of compute resources. This figure is not just over a couple of years, but it's over a relatively long period of time, extending back to 2012. We see plotted a number of very recognizable machine learning breakthroughs, ranging from Elixir in 2012 to VGG in 2014 to AlphaGo up in more recent times. And the pattern is very clear. Every 3 months, we're seeing a double of the compute required to train these networks, or to have them even function. Now, that produces a severe strain on the on us being able to compress these models and have them run locally. If you just consider where this trend might lead, we can see that in the years ahead, machine learning, particularly the latest breakthroughs, might become unaffordable for deployment on ML device, on-device mobile and embedded devices moving forward, as we see this gap between what the models require and what are the different types of compression and efficiency outcomes our techniques can deliver starts to grow wider and wider. Another factor at play is what are the types of machine learning models that will become popular and needed to offer machine learning experiences moving forward. What would be the expectations of an efficient ML device look like in the distant or not so distant future? Well, it seems very clear that machine learning tasks are going to become richer and more powerful. It wouldn't be surprising to see us shift from what is often a classification task, such as recognizing an image or an audio snippet from a relatively constrained set of options, to much more rich machine learning tasks that perform things such as reasoning over those perceptions under sort of open world assumptions using weakly supervised data. What I'm really trying to get at is that the aspirations and the aims of what these machine learning tasks may evolve to be very complex, and the two things that are probably going to support them are the need to have a large number of simple machine learning tasks running all concurrently on the device. Perhaps we might even need 100 of these different types of models to support these large complex tasks. And furthermore, while inference has gotten us a long way, increasingly we see signs that the models we deploy on the device are going to need to have to learn and adapt to be successful. And this is something that we haven't tackled at all significantly so far. And so for these types of concerns, I think it's reasonable to worry that perhaps we're going to have to start to look further afield in terms of the approaches we use to offer and provide efficiency. And so what I want to do in the next phase of this talk is propose very humbly 3 interesting avenues for further intellectual investment towards meeting these challenges and pushing efficient ML even further. I am going to start with an area that I call think different. Now, this direction really pushes us to consider how can we design from scratch machine learning techniques that both balance this need for efficiency and learning objectives. And I want to position it in sharp contrast to the common approach of looking at architectures that come out and then considering how can we compress them or make them more efficient after the fact. To further expand upon this point, I want to draw a loose parallel to the Cambrian explosion that occurred around 500 million years ago. So if you look in the fossil record, there was this point at which the dominant forms of life were all simple single-celled organisms. But after this explosive point, this really inflection point in life, there was a huge increase in the diversity and proliferation of a variety of different types of life forms Now, the connection here is that the basic building blocks of machine learning, so namely, how do we train and set model parameters? How do we describe our models? How do we perform inference? Are actually fairly narrow. They're fairly homogeneous. Even though that we might have devices that have far different types of circumstances to which they want to perform their learning. They might have a wide variety of different types of hardware, but the basic building blocks and how we can realize those are all relatively very, very similar. I believe that there is a need for us to sit down and look for the next 100 or even 1,000 different ways that we can perform inference in radically different ways, or training in radically different ways. Preferably where those different approaches would require different types of resources. Some might require huge amounts of compute but very little memory. Others might have huge amounts of memory in terms of their needs and different types of compute constraints. It would be good to have methodologies that could have different types of success in terms of their learning success depending on when they're being used. We really don't have this sort of rich palette currently, and for this reason I think the sort of overall ambition is of this direction is to really start to invent new Neuralink algorithms where you're focused on offering flexibility and diversity, especially how it relates to the utilization of compute resources. Now I want to talk about one example that would fit under this umbrella. It's a piece of work that we've done over the last couple of years, and to introduce it I'm going to talk very concretely about ResNet 34. Now this architecture does very well in doing vision tasks, but it can be very heavy for some mobile and embedded devices, and this largely stems from the large number of parameters that are needed to describe thousands of different kernels that exist within these different layers. You can think of neural network architectures as Lego buildings. Each of these bricks inside the Lego can be considered kernels, and if you think of neural architectures in this way, our idea in this piece of work is to start to replace individual kernels that comprise a CNN with functions that are cheap to compute and require very few number of parameters relative to the number of parameters that they can then in turn generate. We need to have these functions generate authentic types of kernels that can do the same learning task, but if they're cheap to compute and relatively low in the requirements of their own parameterization, we can have really interesting resource trade-offs. Because if you look in this model design, inference becomes completely different. Normally, if you wanted to use a ResNet 30, you'd need to access all of the individual parameters that describe all the kernels of this model. Instead, under this alternative approach, if you really could describe kernels with classes of functions, you need a far fewer number of learned coefficients that are then provided to these functions. And then you basically, at inference time, you'd inflate these kernels as needed to perform the different operations you needed to pass a single image through the entire network. I'm not going to go through the details in this talk, but essentially we've found a way to perform audio and vision tasks using models of this type. It's founded on the use of orthogonal binary basis, where we can use algorithms like OVSF to cheaply generate these bases used at inference time. We actually call this approach on-the-fly inference to denote how we generate the data structures we require for inference as we go. Now, to exploit the efficiency potential of this model design requires actual hardware support. So recently we developed an accelerator we call Unzip FPGA that can support this approach to designing models. The key factor in its design is the the specialization of logic that can cheaply perform these inflation functions of when you want to inflate a different convolutional kernel that's going to be used in inference time. With this type of hardware support, a model of this type suddenly becomes much more efficient than alternatives. You can incorporate these types of designs not only in FPGA, but you could do so in an ASIC or other types of hardware as well. But I want to focus your attention now on this figure on the left-hand side. This is measuring on the y-axis the speed of inference. X-axis is considering the memory bandwidth of the chip, and we're comparing our method that we call here OVSF50 to a state-of-the-art model pruning method called TAE. The baseline that both our methods are being compared against is a ResNet34 architecture running on a purpose-selected FPGA implementation that will run ResNet34 very efficiently. So this baseline is very fast. It's the equivalent of running a ResNet34 on an accelerator. And what you see here is that the model compression TAE has some modest gains of around 15% speed up in terms of inference speed. But in contrast, our technique is able to provide 94 or 81% increases in inference speed through our model design approach. If you look at the right, you'll see that we're able to achieve this with very little loss in accuracy, a negligible loss in accuracy, in fact, and one that's very similar to that of the TAE model compression approach. And we see this type of approach being, a small sliver of the larger thing that I was referring to earlier as a direction that I call think different. Now, the next direction I wanted to propose and describe is something I call automated specialization. And what it really attempts to do is bring together two very distinct worlds. On the right-hand side is this world of designing efficient hardware and system software and parameterizing it to maximize utilization and the performance of specific types of machine learning models and classes of machine learning models. On the left-hand side is a different world, one where you focus your attention on how you build the models from the ground up. There's a lot of design decisions there as well. You have to think about the architectural decisions of how you want to build your neural networks, the loss functions, the hyperparameters. Now, the problem here is that these two worlds are very hard to bring together. Neither one has any type of systematic way of being aware of the implications of the decisions on the other. What I propose is investigating how we can develop probably what would amount to an ecosystem of design tools that could enable people to enable these tools to not only have a strong awareness of the important factors that exist within these individual domains, but more importantly, facilitate the joint optimization and understanding of how, for example, model decisions can impact performance and how hardware design and software design can then in turn make certain types of models more or less affordable. The broader ambition of this is to enable the automated synthesis of machine learning models that are specialized for a particular task. So they do the task that they're required very well, as well as designed to run on a specific type of hardware very efficiently, perhaps also including the potential of modifying that hardware design to match that automated model that's generated as well. Now, this is obviously an umbrella area with many individual types of challenges to address towards building these types of design tools that could do this type of operation. But what I want to show you is some small steps that we've taken towards this general direction that can, I think, show the value and merit in pursuing it even more aggressively. So specifically in Samsung, we've developed an internal tool called AutoCaml that seeks to perform joint optimization of hardware and neural architecture design. And by bringing these two things together, we hypothesize that we can find architectures that are far more efficient. I'm going to focus on an FPGA example because that's where we have the greatest hardware latitude in terms of options. This is where we should see whether this technique can work or not. We're going to look at how you can use this tool to design a CNN as well as customize the FPGA that it's going to run on. I'm going to quickly sketch out how the system functions. First, there's the design space for the CNNs. This tool, the AutoCaml tool, is going to carefully navigate different options in the way you might design the neural network, select different types of convolutions, wire them up differently together. It'll simultaneously consider different design options in terms of the accelerator design. You can parameterize the different weights in different ways. The PU units that execute the convolutions, you can make them more specialized. You can have different ratios of the different engines. And these two sort of areas, 1 and 2, form design space for both the model and the accelerator that the tool needs to explore. We use, with 3 on-device measurements of different candidates to build predictors that allow us to estimate other candidates at runtime, at search time, to see how well they're going to do, not only in terms of accuracy, but in terms of latency, area, and power. Now, finally, what wraps this together and makes it all work is a design of reinforcement learning, where we use an multi-objective formulation that does something that I haven't seen done before, and that is that it can balance not only accuracy and latency, but also hardware area in the resultant model, all within this one system. Now, to give some evidence that this is an attractive approach, let me show you some results about this tool designing CNNs for a particular Xilinx FPGA. What I really want you to focus in on is the figure on the left, the color-coded annotations indicate 3 different hand-designed solutions produced by Xilinx engineers who understand the hardware very deeply. And you'll see there that for the particular type of hardware design that they instantiate on the FPGA, you'll see a particular level of accuracy for a well-known architecture under this FPGA design. Now, what's notable is all of those black dots that, or black crosses that you see on this figure are automatically found combinations of neural network design and FPGA designs that, when jointly run together, offer trade-offs that are superior to anything found by these expert Xilinx engineers. And this speaks volumes towards the potential for a tool of this kind. Furthermore, if I bring up this one table, what it does is it examines what is the best model that AutoCaml was able to discover in terms of its accuracy, latency, and hardware area required when performing ImageNet compared to what was previously the state-of-the-art for this particular type of FPGA. And what we see is that our automated design tool is able to find not only improvements in latency and hardware area, but interestingly, it's able to also lift the accuracy. So we're able to be more efficient and well as be more accurate through this approach. It's a very interesting result that I think really maps nicely into the potential that I outlined for further exploration of automated specialization. Now, the final area I want to sort of very quickly outline is that called sharing and cooperation. What we see here is something that is an everyday event in New Zealand, where I'm from. We see sheep having to move from one paddock to another, but you'll see what they're doing here is collectively solving this problem together. They're sharing the resources of what they can see, they're coordinating in terms of which sheep should go next, and it's really a remarkable thing to see. Now, as a son of a sheep farmer, I've got to tell you that sheep don't always behave this well and behave this logically. But what I can tell you is this phenomena happens in nature all the time, in birds and fish. But where it doesn't happen yet is in the world of efficient ML. And this direction is pointing out that it needs to. We have examples within the device how machine learning models do not interact well together. I'll show you an example of that. Systems themselves are unable to schedule and optimize the resources of the device to align well with running various types of machine learning models. So there's lack of coordination there. Between devices, there's an absolute lack of cooperation between devices to perform learning operations. There's no real support for this yet, even though that there is obvious, clear limitations and need for further resources. I'm going to very briefly run you through two examples. Let's imagine each of these sheep that you see are individual models all running on a device. Now let me walk you through this example where we have a single device, the sheep we just saw. On that device we have three different models. They're all doing a vision task, each trained to do a distinct vision task. What I've done is I've hidden their final layer, and then we can only see what are the early layers doing. And for these three models, and these are a real three set of models, it actually turns out impossible to tell what is different about them and what tasks they might be doing. If I was in an audience right now, I might ask somebody and say, hey, who wants to hazard a guess about what these different models are doing right now? So you have to just sort of say it to yourself, since I can't hear you. But this is the actual answer. These three models are performing quite different types of classification, elephants facing cars, and yet the only difference you can see between them is in their very final layer. Now, in some sense, this makes sense because vision tasks obviously have to do similar things. So if I'm trying to recognize a car, I need to be able to understand edges, what we see happening in the early stage. But the same thing is true of faces. If I want to recognize a face, I also have to understand edges. But the problem I'm getting at here is that there is no systematic way currently for models to understand these levels of overlap and redundancy between each other and resolve them. There's no sharing of resources. There's no systematic way of doing this yet. And this is just one type of failure where, at least intra-device, we are neglecting potential for sharing resources well and cooperation between our models to do things much more efficiently. Let me give you another example. Instead of thinking of these sheep as individual models running our device, think of them as individual devices all doing learning tasks. The problem today is that there's very little support, if any at all, in how devices can come together to perform machine learning tasks. In the literature, there has been a few examples of people proposing methods to do this, but thus far they haven't been really applied in practice. But what I think we're going to see happen moving forward is that as we want our devices to perform not just inference but learning, and we start to realize how short of hardware this forces us into being in, combined with the fact that devices are going to need to share data if we're going to start to be able to also start to train and adapt our models, we're going to see the need for cooperation between our devices increase markedly. And towards this, I would point out one piece of work that we've been doing lately. We've developed a system, completely open source, and we're trying to build a community around it called Flower, which is really trying to facilitate the federating of learning between machine learning models on embedded and mobile devices. Now, one thing I'd point out that we've realized since building and experimenting with Flower is that there is really an underappreciated problem in performing collaborative forms of learning like federated learning. And that is, as we see increased amounts of heterogeneity between devices, these learning algorithms behave worse and worse. And so the simple example I'm showing you here on the left-hand side is the amount of time it takes to train a well-known machine learning data set out of Fashion MNIST. We're using NVIDIA embedded GPUs, and we're considering 2 situations for around 50 different collaborating devices. And the red bars, all those devices are completely homogeneous. They are able to use all of their GPUs. And then in the blue line is the exact same setup, but for just one single device, 1 in 50, we disabled its GPU. It had to use its CPU, so it suddenly became imbalanced. What happened is that training time jumps markedly, a 3.5 times increase just through what is a very tiny amount of heterogeneity within the client pool. This speaks directly to the difficulties that we're going to face as we build out and further explore how devices can collaborate together, even though that I feel that this is going to be a necessary bridge to cross if we're going to have deeper and deeper amounts of efficient ML spread throughout our devices. Now, this concludes the 3 directions that I really want to highlight in this talk. And I really think these things are going to be necessary for us to be able to maintain the types of progress we've grown accustomed to. But before I move on to the final part of the talk, I wanted to add one more thing, and that is, of course, I can't say all of this and neglect the area of hardware. I don't have time to go into this, but of course hardware is going to play a strong role in the evolution of efficient ML. I can see some really important avenues such as increased use of analog compute. I think there are some fascinating things to be done in terms of placing more compute right next to or inside the different types of sensors that we're trying to use, in particular image sensors, but others as well. And then I think the types of tools that I've discussed in terms of automated specialization can play a key role in how hardware also evolves, because it can provide greater facility for performing co-design between hardware and the models themselves. So that's all I'll say on the topic, but definitely hardware is going to play an important role. And I'm going to close this talk with a series of fun predictions about where I see efficient ML potentially ending up. And then in the question time, you can tell me why I'm completely wrong. So prediction number 1, this really comes from a place where it would be completely reasonable to say, well, after 4 or 5 years of research, and in particular some of the interesting outcomes that you discussed at the start of this talk, really, is this it for efficient ML in terms of a research direction? Have we discovered all the things we're going to discover? I'd hope this talk has dissuaded you from this notion, but it might be reasonable to hold it. And my response would be that I think we're going to see on-device machine learning or efficient machine learning go far beyond what we see it doing today, and go far beyond what is a very classification-centric view of the world. The next steps of where on-device machine learning will go is to reach beyond classification to where classification and perception, sort of pattern recognition of sensory inputs like image and audio and so on, really become just the very lowest level building block of what is and what becomes a far richer stack of learning components that drive smart devices to be truly smart. And what I mean by this is that there's going to be a need and expectation for us to be able to support various types of understanding between these things that the smart devices are able to perceive. There'll be interest in enabling these devices to start to reason about what it's perceiving and the understanding of the context. There's going to be the need for it to have some level of common sense so it can start to act and react rationally within the environments it sees. And the thing I'd really focus our attention on is that obviously there's some difficult machine learning problems to be solved for us to realize these types of models, but moreover, we're also going to have to find a way to make these things also run on the device and just as efficient as we do today for what would be comparatively a much simpler type of task of perception. Now, that is prediction number one. Number two is that we're going to see a meeting in the middle of efficient models and state-of-the-art accuracy, particularly at the start of this area. There was always this notion that you had to trade off accuracy to make something efficient, but I think that time has passed. If you look at this figure here that I took from an ICML paper in 2019, where the authors proposed a model design called EfficientNet. What was interesting and relevant about EfficientNet is that not only did it offer high levels of accuracy compared to the other types of models that it was compared against, well, not only higher, but the highest level of accuracy, it also offered the best, lowest levels of model size and relating efficiency. So it was the most efficient and the most accurate. And I think this is a trend that we're going to see happen more and more moving forward. The reason for this is that increasingly I feel that efficient models, the ones that we're trying to develop here in mobile computing, are also going to have an unfair advantage over their inefficient cousins. You just have to think about how fast they will enable people to explore and experiment. If they can train these models very fast, they can try out a lot of different variations as they move through the design space of their ideas. But more importantly, efficient models are also going to be those sort of models that you can scale up to be larger and larger architectures or consume larger and larger amounts of data. It's for these types of reasons I think that we're going to see increasingly model designs that are both efficient but also offer the best of the best accuracy available. Now, the final prediction I want to leave you with is probably the biggest one. It suggests that in the future, perhaps the near future, perhaps we can see devices such as mobile devices, such as embedded devices, replacing data centers as the core, as the heart of machine learning. Now, I'm not going completely crazy. Of course, data centers will still have a big role for many different types of use cases for machine learning. Corporations are still going to analyze their data. Scientists are going to want to analyze their data to understand what's going on in the physical world. But there is going to be, I think, common types of systems, such as the systems that are used by consumers, the systems that we deploy in our homes, the systems that are deployed in dynamic environments, such as those that are investigated by robots and drones, whereby mobile and edge devices are not only going to be responsible for doing inference, as they increasingly are today, but they're also going to be responsible for training. Now, one key fork in the road is going to be on us. It's going to be, can we develop and devise techniques that allow singular devices in some cases, or more likely large collections of devices, to consume data and improve their models to a degree that is comparable or at least passable in comparison to data centers. So that's going to be a big question to us. Basically, can we enable mobile devices to participate in these types of problems effectively? But the second and critical point is when we start to see learning algorithms that are able to convincingly consume and leverage unlabeled data. Because once we see that, then the value of data that these edge devices, these mobile devices have will become enormous. The devices that they already are in their environment. As they capture information, they're going to be already in the domain. The data they capture is going to be plentiful. It's going to capture changes such as new objects arriving, other objects removing, and so on. So the value of this edge-sourced information is going to be critical, and once we have algorithms that can leverage the information and incorporate it into the models, it's going to become even more so. And perhaps we'll get to a point where it no longer even becomes feasible because of the sheer volume of edge data to move all of it into the data center for models to be trained, and rather it may make much more sense to perform efficient forms of training through collections of devices all running locally on the edge. Now this would be a complete change in sort of the mindset of machine learning, where we really put data center at the heart of everything. But it's a plausible one, depending on how it falls out. And I think it's really fascinating to see how our community can play a key role in seeing if it happens to come to fruition. Now, with that, I'd like to thank you very much for your time and listening to me today. I've listed here on the slide a number of papers that I touched upon during this talk, and with that, I'm very happy to take questions.